Morning, everyone. Today we're going to talk about notes on common overall shapes of distributions. This is the first S, I guess it doesn't matter which S we talk about, in the SOX acronym that you learned about in your last set of notes. When we describe a data set, we need to think about four very important things: the shape of the distribution, the possibility of outliers, the measures of center or average in the data set, and the spread of the data or the variation in the data. And the notes today are focused on the shape of the distribution. So the big picture here is that we like to recognize patterns, right? And displaying a data set is a great way to see if there are any patterns in the data that we can learn from. We're studying the overall shape of these distributions, so here's some of the common ones that you should recognize. The first one is a uniform distribution. It says frequencies of different classes are equal, or approximately equal. They're not always exactly equal. And one image you might use to remember what a uniform distribution is a perfectly aligned row of bottom teeth. It's one highly eccentric person's image. So if you imagine this graph here as a row of bottom teeth or a picket fence, something where the heights of each bar in the histogram are the same height. This would be called a uniform distribution. An example of that would be rolling die. A discrete example would be rolling one die and the results. Since the probability of rolling any one of the 6 numbers on a standard die is equal, 1/6, if you rolled that die many, many times, then the frequency of 1s, 2s, 3s, 4s, 5s, and 6s would be the same. And you would get a uniform distribution of the results of rolling one die. And that's what you see in this second example here in green. So these would be 1s, 2s, 3s, 4s, 5s, 6s. And remember, a histogram uses the class boundaries as marks on the horizontal axis, so that there's no chance that a 1 could fall in any other category but that first bar between 0.5 and 1.5. Same for a 2 and so on. A continuous example of a uniform distribution might be a frequency of airport shuttles for a popular hotel. So if we have any, of course the horizontal axis is time, so it's a continuous variable. Any time could work for a shuttle going to and from the airport. Probably on a strict schedule, but it's not always the exact time. And the shuttles are going out regularly between each of those hours. And so the number of shuttles that go to the airport between 8 o'clock and 5 o'clock is approximately equal by hour. That would be a continuous example of a uniform distribution. The next distribution we're going to talk about is probably the star of the show, the normal distribution. We'll spend a lot of time with this guy. This is an introduction. Describing the distribution or the shape of the distribution, you would say that frequencies are small at the extremes, the low and the high end, and large at the center. It's symmetric. It's a continuous distribution, but it can be used as an approximate model for many discrete distributions. We'll look at one of those in a second. And the image here would be the bell, the famous bell curve, or a conventional hairdo. It can be flatter, it can be taller, as long as most of the data is centered and it's symmetric on both sides with very little data at the extremes. Normal distribution. Here's a discrete example. If you were to roll 2 dice, one die is a die, 2 die is a dice. Anyway, if you were to roll 2 dice and sum the results, you can see that most often you would get 14. And the reason for that is it's most probable that you would roll a 7 if you summed 2 dice. Oh, sorry, I said 2 dice. This is 4 dice. So if you roll 2 dice, it's most probable that the resulting sum would be a 7. Therefore, if you rolled 4 dice, it's most probable that the resulting sum would be 7 and 7, 14. Much less probable that you would get 24 or 4, because that would mean you've got 4 6s or 4 1s, which is improbable to get. Okay, so this is a discrete example of a normal distribution. You can't get any fractional numbers here. You can only get whole numbers when you're summing 4 dice. Okay, a continuous example of the normal distribution would be the masses of can't talk this morning. The masses of pennies manufactured in 2016. And you can see that the variation is not great. We have 2.425 to 2.575 grams. So you're not going to have many pennies in the lower end. You're not going to have many pennies in the higher end. Most of your pennies, I missed it. Try again. I want to have my mean in the 2.5 area. That's a little better. Most of your pennies will be centered around the mean. In this case, it looks like about 2.5 grams, because they're manufactured with low tolerance to be outside of that mass. And that's why you'd have few pennies at the extremes and most of your pennies centered around the mean. Normal distribution, continuous example. Okay, well, if we don't have symmetry in the distribution, we might have skew. Most of the data may be collected to the right, or most of the data may be collected to the left. Therefore, it's asymmetric. The variation is restricted on one side. So we'll talk about that in a minute. If you have restriction in one side to the low end or the high end, then your data will tend to collect there, and there'll be less and less data as you move away from that restricted side, whether it's the right or the left. So if we're skewed to the right, and our tail is to the right, most of the data is collected on the left. In that case, the mean would be drawn forward or drawn greater, so the mean is greater than the median, except in rare cases. If it's skewed to the left, the tail is to the left, and the mean will be drawn to the lower end, so the mean would be less than the median, except in rare cases. So here's a discrete example of skew left. More of our data is to the right. Now in this case, it does have, for quiz grades, it does have a limit on both ends, 0 to 25. However, in a class of bright young people, you're going to have most of your grades clustered toward the higher end, and you'll have fewer grades in the lower end. This is a discrete example because you can only get between 5 and 25 points, or 0 and 25 points by 5s. Skew left. And a continuous example might be the time before a light bulb burns out, which would be skew to the right, which means that our tail will be to the right, so less data to the right, which makes sense because we've got a limit to the left side of 0. But in theory, the right side, a light bulb could last a long, long time. So we'll have many more light bulbs that don't last as long, and then as time carries on, we'll have fewer and fewer and fewer light bulbs lasting that long. So our data will be collected to the left, and since time is a continuous variable, this is a continuous distribution representing skew right. And in this case, again, the mean would be drawn to the higher end because of the data. To the right, some of those light bulbs that last longer, so the mean would be to the right of the median here. And those are the notes for common overall shapes. Think distribution or shape in our SOX acronym. Have a good day, guys.